is called the ideal if U is a subgroup of R under the addition, and U is for every U belongs to U and R belongs to R. The U are both UR and RU belongs to U. This is the basic definition. So what are the key properties of that? That is the additive closure. Ideally is U comma V. Now obviously U plus V belongs to U. And additive inverse U is belongs to U. The minus U. So U and R belongs to R. That is U or this is called the absorption property. U is belongs to U and R is belongs to R. That is called the UR belongs to R or U belongs to R. So the ideals are two-sided by the definition of the absorption multiplication from both sides. So that is called the two-sided ideal. Otherwise, the one-sided ideal, left ideal and right ideal. So it's a very basic definition ideal. That means absorption property plus the construction of quotient ring that is the So this is the definition of the ideal. So that is the absorption property satisfied now or a subgroup of the ring R, that is called under that is called a subgroup of ring R under addition and satisfy this absorption property, that is called the ideal. And construction of quotient ring into the given ideal U of R, the constructed quotient ring R by U. Already we know that in the group theory. So elements R by U are cosets, that is the here left coset, that is A plus U is defined as the collection of A plus U, U belongs to U, and addition, how to define the addition, that means A plus B plus U. So the quotient ring R by U plus is already an abelian group, from the group theory. And the multiplication of in R by U, how to define the multiplication, that is the AB plus U, as usual like that A plus B, A plus U plus B plus U, addition will be defined the same way we can define the multiplication. And well defined as for the multiplication, that is A plus U is equivalent to A dash plus U, B plus U equal to B dash plus U. So we can define the AB plus U is obviously equivalent to A dash B dash plus U. So at a natural homomorphism, that is the phi from R to R by U is defined as defined pi of A equal to A plus U is a ring homomorphism with the kernel U, that is R2. It's a natural homomorphism. So pi of A is defined as A plus U with the ring homomorphism and with the kernel U. And already we know that about the definition of the kernel U. And U is an ideal of the ring R. U is an ideal of the ring R. Then R by U is the ring and is a homomorphic image of R. For example, NZ is an ideal of Z. NZ is an ideal of Z. Then Z by NZ is a isomorphic to Zn. Z by N is isomorphic to Zn, and R is a ring, R is any ring, and 0 and R itself are always ideals. The kernel of any homomorphism is an ideal. Kernel of any homomorphism is an ideal. and these are some properties. Fundamental theorem of ring homomorphism, R dash as the ring and pi a homomorphism of R into R onto R dash with the kernel U. Then these R dash and R by U are isomorphic because of natural homomorphism from R to R by U, so that here R dash R and R dash is the ring homomorphism with kernel U, so that R dash is isomorphic to R by U. So there is a one-to-one correspondence between the ideal of R dash and the ideal of R that contain the U. That contain U, and also W dash is an ideal of R dash. Then W is defined as the collection of x belongs to R, the pi of x belongs to W dash. Then R by W is isomorphic to R dash by W. Okay, these are some results. That is called the fundamental theorem of ring homomorphism. It's a very simple idea. And some problem, U is an ideal of R. U is an ideal of R, and 1 belongs to U. 1 belongs to U. U is an ideal of R. Then U is equal to R. So how to get the U equal to R? The U is an ideal. 1 belongs to U. So for any R belongs to R, by the definition of the ideal, so R into 1 belongs to U. R into 1 belongs to U. That means R is belongs to U. So for every R belongs to R, the R is belongs to U. Now the obviously belongs to U equal to, okay, U equal to R for every element of R. It's a very simple idea. And F is the field. F is the field. Then F is the field. Then its only ideals are 0 and F only. Okay, F into the field are the ideals are only 0 and F itself. So U is an ideal of U. Na, that is, if U equal to 0 now, okay, U equal to 0, obviously U be an ideal of F. Otherwise, suppose U contains some non-zero element, that is A belongs to U, that is A is not equal to 0. Since F is a field, A has a multiplicative inverse, that is A inverse belongs to F. Okay, a field means the every non-zero element has a multiplicative inverse. So the 1 equal to A into A inverse, that is belongs to U. Because U is an ideal, by absorption of multiplication, A into A inverse belongs to U. So therefore, when you apply the problem 1, that is 1 is belongs to U, now U equal to F. U should be equal to F. So from this, what is the conclusion? The ideals are 0 and F only. The ideals are 0 and F only. So very simple proof. Okay, so you can understand and take in memory. So and another one is prove that any homomorphism of a field, is either an isomorphism or takes each element into 0, Here pi from F to R is a homomorphism from a field F to some ring R with the kernel of U. How to define? That is the kernel of pi. Kernel of pi is called the kernel of U. Consider the kernel of U equal to kernel of pi, which is the ideal of F, So when you apply the previous problem, the only ideal for the field, the only ideals of the field are 0 and F itself. If you take U equal to 0, then pi is injective, pi is also surjective onto images. If pi is also surjective onto its image, where it is an isomorphism onto pi of F. It is an isomorphism to pi of F, and therefore U equal to, if you take in the case U equal to F, pi of A equal to 0 for all A belongs to F, then pi is a 0 homomorphism. There are no other possibilities because of these are only the ideals of f. So only these two possibilities. Therefore, the homomorphism of the field is either isomorphism or takes each value into 0. Each value into 0. And R is a commutative ring and A belongs to R. R is a commutative ring and A belongs to R. Suppose AR is defined as the collection of the R belongs to R is two-sided ideal of R. This is the only one-sided, single-sided like that, but this is the two-sided ideal of R. So how to prove this is how to verify this condition. Already that is A into 0, 0 belongs to AR. Obviously, because of for every R belongs to R, AR is the collection of AR. So 0 is the A into 0, that is 0 is the element, this is equal to 0, 0 belongs to AR. So that R is not equal to 0, R is not equal to 0. So when prove the additive subgroup for the ideal, AR1, AR2 belongs to AR, that is the sum is AR1 plus AR2, the A into R1 plus R2 obviously belongs to AR. So and the inverse, that is AR belongs to R, for every AR belongs to R, minus of the inverse is minus AR is obviously A into minus R, that is belongs to AR. So for come to the absorption property, that means for any AR belongs to AR and S is belongs to R, I will try to prove the ARS and SAR both are belongs to AR. The right absorption and this is the left absorption, that is AR into S, A into RS. R is belongs to R, S is belongs to R, that is A belongs to AR. SAR is SA into R, that is SA is equivalent to AS. SA equal to AS, this is the commutativity. So AS into R, this is we can write A into SR, that is obviously belongs to once again AR, belongs to AR. Therefore AR is the two-sided ideal. When you define the AR like that, that is the two-sided ideal. And this is by the example. This may be false if R is not commutative. R is not commutative, this is false. So for example, R is M2R, that is a collection of 2 bit matrices, real matrices. And when you choose the A equal to the collection AN 1000, then when you define the AR like that, 10XYZW, that is the collection AR for XYZ. When you multiply it, that is XY00, X comma Y belongs to R. When you take B equal to 0010, this is M is 1000, this is belongs to AR, and this is belongs to R, B is belongs to R. Then BM is, when you multiply it, the collection like this, but this is not belongs to AR, this is not belongs to AR. So in the case of R is not commutative, then that AR, the collection of AR, may not be two-sided ideal. And another one, U and V are ideals of R, and U plus V equal to the collection of U plus V. Prove that the U plus V is also an ideal. Okay, very simple. Ideal means that is U plus V, first of all, satisfy the additive subgroup. That is, the additive subgroup means the closure and inverse is exist, and then absorption property. So this is try to prove that ideal of R, then the first of all U and V ideals, so that 0 belongs to U, 0 belongs to V, that is 0 equal to 0 plus 0 obviously belongs to U plus V, that is the ideal element. And additive subgroup proof the பண்ணுறதுக்கு ரெண்டு எலமெண்ட் when you take the u1 plus v1 u2 plus v2 ரெண்டு எலமெண்ட் நீங்கள் எடுத்துக்கிட்டிங்கன்னா ரெண்டுத்தையும் ஆட் பண்ணும்போது க்ளோஷர் ப்ராப்பர்ட்டி பார்த்தீங்கன்னா obviously u1 plus u2 v1 plus v2 இந்த structure belongs to u plus v because of this is belongs to u, this is belongs to v, because of u and v ன்றது ஐடியல்ன்றதுனால இதனுடைய இன்வர்ஸ் பார்த்தீங்கன்னா additive inverse negative of something, so minus u minus v, so both are belongs to something. So now come to the absorption property, that is the absorption property means just இது மட்டும் இருக்கான்னு கூட செக் பண்ண போதும், that is u plus v belongs to u plus v, r belongs to r, so r into u plus v into r, so that is the ru rv ன்னு வந்துரும், that is ru belongs to v because of u and rv belongs to v because of both are ideal. இது both are ideal ன்றதுனால this is belongs to u plus v, so u plus v is an ideal, so very simple proof. Okay, so u plus v is an ideal, so uv ideals, then u into v be the set of all elements that can be written as the finite sum of elements of the form uv, u belongs to v and v belongs to v. Prove that uv is an ideal of r, uv is an ideal of r, then uv is the additive group, so x comma y in red element எடுத்தீங்கன்னா that is the product of elements, and x plus y is obviously belongs to the is also finite sum of the product of uv, that is belongs to uv. The same way inverse additive inverse is also belongs to uv when expressed like this, and absorption property is also true because of the u and v is are ideal, so absorption property x is belongs to uv and r is belongs to r, then I will try to rx means this is rx, so ru1 and u is ideal, so that is ru1 like that. The same way xr multiply பண்ணும்போது v1r vnr is belongs to v, so this is belongs to uv, so uv is an ideal. Okay, so and also uv is the subset of u intersection v, so when you choose the some element in uv is in the form of like this, ui belongs to u, vi belongs to v, and u is an ideal of ideal, vi belongs to r, and therefore ui vi belongs to u because of u is an ideal, and x belongs to u, and x belongs to u, that is as u is closed under addition, so v is an ideal of ideal, ui belongs to r, so that is ui vi belongs to v for each I, that is therefore x belongs to v, therefore x is belongs to both u and v, that is the intersection is also contained the x, so uv is the subset of u intersection v. So in the case of r is the ring of integers, u is an ideal consisting of multiple of 17, then if v is an ideal of r, the u is contains v is contains u, then either v equal to r or v equal to u, that is ideal. So z is ideal, that is given that a ring of integers, every ideal is a principle, that is v equal to generated by d for some d belongs to z, and u equal to it's a multiple of 17, that is the subset of v, which is equal to d, so d divides 17 is a prime number, only positive divisor 1 and 17, so v equal to 1 and v equal to 17, v equal to 1 means that is generated by z, that is equal to r, 17 is u. Okay, this is the example. So R is a principal ideal domain, that is u equal to generated by p. P is an irreducible elements, ideal v, u is v equal to u and v equal to r v equal to r. The same way the u is an ideal of r, then r of u is defined as the collection of elements of the ring element if satisfying the x equal to 0 for all u belongs to u. For all u belongs to u, then r of u is an ideal. So ideal நம்ம already prove பண்ணிருக்கோம் like this. We can in the definition use பண்ணி அது ideal நம்ம check பண்ணலாம் in case of கேட்டாங்கன்னா. So the ideal of R of U, R over U is defined as the collection of X belongs to R, that Rx belongs to U, Rx belongs to U, that is for every R belongs to R. So the R over U is an ideal of R, then it contains U. இதுவும் அந்த டெஃபினேஷன் யூஸ் பண்ணி ப்ரூவ் பண்ணலாம். ஜஸ்ட் சப்குரூப்னு ப்ரூவ் பண்ணால் அண்ட் அப்சர்ப்ஷன் ப்ராப்பர்ட்டி செக் பண்ணணும் பர்டிகுலராக. The product UV is an important ideal arithmetic, that is number theory. The R of U defined as annihilator. R of U is called the annihilator of U. And R over U is called the colon ideal or ideal quotient அப்படின்னு சொல்லுவாங்க. இது மாதிரி or be the ring with unit element, define the or cap or tilde or power tilde with operator A in circle plus B equal to A plus B plus 1 and A into B, AB plus A plus B, where right hand operators are those of R. So the first of all, this or power tilde is a ring. You can prove the properties by the properties. It's a very simple properties. So நீங்கள் செக் பண்ணலாம் ஈஸியாக ரிங்கா ஐடியலா அப்படின்றது by the definition. And also both are R and R power tilde is a homomorphism and isomorphism. So that is when you define the pi of x equal to x minus 1 like that. And the ring of rationals of rational 2 by 2 matrices. That means 2 by 2 matrices contains only the rational numbers. As no non-trivial ideal. That means that ideals of the collection of ring of 2 by 2 matrices with rational entries, only the trivial ideals. That means that set is ideal or identity elementary is ideal. Okay, for example, suppose I is non-zero ideal நீங்கள் எடுக்கும்போது, that is A belongs to I be non-zero. So that is the elementary row and column operation using the invertible matrices. Since I is an ideal now, for any invertible matrices PQ belongs to R, PAQ belongs to I. So we can transform A into the matrix with a 1 in the some position and 0 elsewhere. The further multiplication we can obtain the elementary matrices. By further multiplication we can obtain the all elementary matrices. Hence all the matrices in R, this is the all matrices in R, therefore I should be equal to R. Therefore the set of matrices 2 by 2 matrices with rational entries has no non-trivial ideal. So only trivial ideals are there. Okay. And the quaternion over ZP. So the quaternion over ZP, P is the odd prime. In the form of the alpha naught plus alpha 1i plus alpha 2j alpha 3k. Group theory பார்த்திருக்கோம், alpha I belongs to ZP. So it's a ring with p power 4 elements. This is the ring with p power 4 elements. When you define over ZP, P is odd prime. So and only trivial ideals. This is also contained only trivial ideals. And set of all 2 by 2 matrices with rational entries is also as only trivial ideals. Okay. And also it is not a division ring. That means we can find out the zero divisor in this one. In ZP there exists the non-zero elements whose square sum to 0 modulo P. So by quadratic reciprocity, that is P congruent to 1 modulo 4, and there exists x comma y with x square plus y square equal to 0 modulo P. So Q equal to x plus iy and Q bar equal to that is x square plus y square. This should be equal to 0 because of which is implies Q is a 0 divisor. So therefore, it's this quaternion over ZP is not a division ring. It's not a division ring. Already நேத்தே நிறைய example பார்த்திருப்போம். And RA, this is a left ideal. The RA is a left ideal. That is left ideal means that its property is satisfied that xk belongs to R and R belongs to R. Xa belongs to RA, that is R into that ring element in the left only, not only in the right. So not on the right. So R into Xa equal to Rx into A. Rx is obviously belongs to Rx into A is obviously belongs to Ra. So therefore Ra is the left ideal. The intersection of two left ideals is the left ideal. Intersection of two left ideals is left ideal. So just very easy to check. Okay, and the group property and then left ideal properties. The ring element is should be in the left. R belongs to R, A belongs to L. So A belongs to L1 and A belongs to L2. Then RA belongs to L1, RA belongs to L2. That means RA belongs to L. So L is the left ideal. That is intersection of two left ideal is a left ideal. So the matrix is called the simple ring here. Matrix rings over the field or simple rings, that is non-trivial ideals, no non-trivial ideals. This is the example. Intersection of left ideal and intersection of left ideal and right ideal of R. So what about that L is the left ideal, R is the right ideal. The intersection is called, I give the name I. So I is certainly an additive subgroup, and I may be not left ideal or right ideal. So that is called that I is what's called, that is the two-sided ideal. If all and L and R both two-sided, that is for counter example for the non-commutative ring. For the non-commutative ring, the intersection of the left and right ideal, for example in M to R, L equal to A comma B, L equal to the collection of the elements like this 2-bit matrices A, B, 0, 0, A comma B belongs to R, that is the left ideal, and this is the right ideal. The intersection should be is in the form of this one. Intersection A0, 0, 0. So the intersection is not a left ideal or right ideal in M to R. If one of them is a two-sided, then the intersection is one-sided property from the other. Okay, that is a very important point. Okay, so that is the intersection is a one-sided property from the other. And R of A is defined like that. R is the ring, A belongs to R. R of A is a collection of the ring elements, Ax equal to 0, and this is like that defined, R of A. Then R of A is the right ideal of R. And L is the left ideal of R. And the lambda of L is defined that collection of the ring element, and Xa equal to 0 for every A belongs to L. Then lambda of L is two-sided ideal of R. Okay. It's a very simple. I hope you are understand how to verify the ideal property. So then R be a ring in which x cube equal to x for every x belongs to R. R into the ring, x cube equal to x for every x belongs to R. Then R is called the commutative. R is called commutative. Okay, that is x cube equal to x. This implies that the x square is idempotent. What do you mean the idempotent? That is x square whole square. That is x power 4. X power 4 we can express x cube into x. அப்படின்னா x into x வந்துடும். ஏன்னா x cube equal to xன்றதுனால this is x square. So x square whole square equal to x square. And show that this is 2x equal to 0 for every x belongs to R because of x plus x whole cube equal to x plus x. So x plus x whole cube equal to 8x cube. 8x cube na this is equal to 8x. 8x into the x plus x 2x. Okay, from this 8x equal to 2x means 8x equal to 2x, that means that is equal to 6x equal to 0. That means x plus x square. Therefore this is equal to 2x equal to 0. And that x plus x square whole cube equal to x plus x square. The relation eventually that is forced to, that is equivalent to 2x equal to 0. So that means the right ring has a characteristic 2. That means ring has characteristic 2. So the x comma y for every element x comma y belongs to R. The x plus y whole cube equal to x plus y. Because of the x cube equal to x, y cube equal to y, when you apply here, then x plus y equal to this is equal to 0. And similarly x minus y whole cube equal to x minus y gives another equation, that is xy equal to yx. Therefore this is that is the commutativity. Okay, or be a ring with homomorphism with unit element so R be a ring with unit element 1 and pi is a homomorphism of R into R and to R dash. So then pi of 1 is the unit element. Pi of 1 is the unit element. Unit element means there exists some other element. When the product is, we get the same element, that is the pi of 1 into y equal to pi of 1 into pi of x, that is y is pi of x equal to y. So then that is equal to pi of 1x, that is equal to, because of its homomorphism, equal to 1. This is example. And more ideals, that is the or be a commutative ring, or be a commutative ring with unit element whose only ideals are 0 and R itself, then R is a field. Already field க்கு வந்து only trivial ideal இருக்கும் அப்படினு பார்த்தோம். ரெண்டு எக்ஸாம்பிள் பார்த்தோம். ஓகே, அதுக்கெல்லாம் வந்து only trivial ideals, non trivial ideals கிடையாதுன்னு அந்த எக்ஸாம்பிள்லாம் ஞாபகம் வச்சுக்கலாம் for this lemma statement னுடைய application. Then that is ஒரு commutative ring with unit element whose only ideals are 0 and R மட்டும்தானா, that is no non trivial ideals, then that commutative ring is called the field. For a commutative ring R with unity, that is a commutative ring with unity, that is following or equivalent, that means R is a field, then the only ideals are R and 0, ideals of R 0 and R, and every non-zero homomorphism from R is injective. Homomorphism R is injective. இது மூணுமே equivalent statement. Okay, that is R is a field, every non-zero homomorphism from R is injective. From R is injective. இது பார்த்தோம் already, that is the only ideals 0 and F in the case of the field. And consider Z, it has a non-trivial ideals like 2Z, it is not a field. Okay, Z is it's a non-trivial ideal, it has the non-trivial ideals 2Z, then it is not a field. The matrix ring has only trivial ideals, but it's not commutative. So the commutative hypothesis is essential. Okay. So the converse of the lemma is also true. If R is a field, then it's only the 0 and R are ideals. Non-commutative ring means the ring R is called the simple. The ring R is called the simple if it's only the two-sided ideals are 0 and R. The field is simple but not necessarily a division ring. So the definition of the maximal ideal, it's a very important concept. The definition of the maximal ideal, so the ideal M is not equal to R in a ring R is said to be maximal ideal if whenever U is an ideal of R, then such that M is the subset of U, U is the subset of R. Then R equal to U or M equal to U. When R equal to U or M equal to U, that exists an ideal, that is called the maximal ideal. Am I correct? So that is that exists ideal. Some ideal is called the maximal ideal means with the condition that is M is subset of U, that is R equal to U or M equal to U. R equal to U or M equal to U. So that is M must be the proper ideal. And the M is a maximal if there are no intermediate ideals between the M and the R. The maximal ideal, that's all idea. That is no intermediate ideals between the M and R kidayila nadula or ideal varadu appdinu artham. That is called the maximal ideal. And the condition M is subset of U, U is the subset of R, U is an ideal. Then U equal to M, suppose irundhadana U equal to M irukum illa U equal to R irukum. Okay. So the maximal ideal means ideal kidayila endha ideal irukadunal. Not every ring has a maximal ideals. So R as a unit element, then the maximal ideals exist. R as unit element, then the maximal ideal is exist in artham. That is using Jones lemma, axiomatic choice. A ring can have many different maximal ideals. The 0 ring R equal to 0 has no maximal ideal. These are very important points. And the structure of ideals in Z. Structure of ideals in Z is of the form, Z is since Z is the principal ideal domain. Every ideal is of the form in the set of integers is of the form U equal to the collection of N naught, that is generated by N naught, that is the collection of K N naught. K is some integer. For some integer N naught greater than or equal to 0. P is a prime ideals or maximal ideal. What do you mean the prime ideal? That is P is a prime number. Then capital P is generated by the prime number P is a maximal ideal of Z. Is a maximal ideal of Z. M equal to N naught generated by some integers is a maximal ideal of Z. Then maximal ideal of Z then N naught is a prime number. N naught is a prime number. This is the important one. And the characterization of Z in a ring of integers Z, the maximal ideals are exactly the ideals of ideals P. Okay, ideals, the maximal ideals are exactly the ideals P where P is a prime number. The prime ideals are exactly the ideals P that is generated by P where P is a prime number plus the 0 ideal. Every maximal ideal is a prime ideal, but not every prime ideal is a maximal ideal. So 0 is a prime ideal but not maximal ideal. Okay, this is also a very important one. So the 0 ideal forms 0, for example 0, the collection of prime but not a maximal ideal, that is the form 0 and example 0, and maximal and prime both, that is generated by some prime number, for example 2, 3, 5 and so on. Non-prime ideal, for example generated by some positive number, that is a composite number. This is the non-prime ideal, not a prime ideal. Okay. Connection with the quotient ring, that is an ideally m of the commutative ring or with unity is maximal if and only if R by m is a field. It's a very important one. Okay, most of the competitive exam கேட்கக்கூடிய ஒரு idea. The ideally m of the commutative ring R with unity is maximal. So m is the maximal ideal. M is the maximal ideal for the commutative ring with unity if and only if R by m is the field. R by m is the field. So for example, m equal to p is a prime number. Then z by p is isomorphic to zp. Zp is a field. Zp is a field. And I equal to n is a composite number. So z by n as a zero divisor and is not a field. So maximal ideal in continuous functions. So C of 0, 1 means collection of continuous function in 0, 1. So R be the ring of all real valued continuous function on the closed unit interval 0, 1. So to construct a maximal ideal, that is for each gamma belongs to 0, 1, define the m gamma, the collection of the function f of x, that's f of gamma equal to 0. What are the conditions? F of gamma equal to 0. So then that is called the maximal ideal, the m gamma. And R is a commutative ring and with unit element m is an ideal of R. Then if and only if m is maximal ideal and if and only if R by m is a field. We already discussed பண்ணிட்டோம்னு நினைக்கிறேன். Once again the same structure. So already the continuous function from 0 to 1 is a field, that is divided by m gamma is the isomorphic to R, isomorphic to set of real number R, that is this is a field. So m plus the isomorphism sense f plus m gamma, this is 2 f of gamma, that is because of f is isomorphic to g modulus of m gamma, the f of gamma equal to g of gamma. Or be the ring with unit element, or is not necessarily commutative, such that only the right ideals of R, 0 and R, then R is a division ring. R is a division ring. R into the ring with unit element, this is not a commutative ring, and only right ideals of R, 0 and R only, that is a trivial right ideals, then R is called the division ring. R is a division ring. So we can prove easily, this is a very simple concept. R be the ring, only the right ideals are at 0, then R is a division ring, or R is a ring with prime number of elements in which a b equal to 0 for every a comma b belongs to R. So J be the ring of integers, P is a prime number, and P is the generated by P is the ideal of J consisting of all multiple of P. Then J by P is isomorphic to Jp. So we can define the function from J to Jp, that is phi of n equal to n modulo P. So that is well defined, that pi of n equal to pi of m. And homomorphism condition, what is the homomorphism condition? Because of the ring contains the two operations, group theory பார்த்தீங்கன்னா ஒரே ஒரு ஆப்ரேஷன் தான் இருக்கும். இங்கே வந்து பார்த்தீங்கன்னா ரெண்டு ஆப்ரேஷன் இருக்கும், ப்ளஸ் அண்டு டாட். பை ஆஃப் என் ப்ளஸ் எம் ஈக்குவல் டு பை ஆஃப் என் இன்ட்டு பை ஆஃப் என் ப்ளஸ் பை ஆஃப் எம், பை ஆஃப் என் ப்ளஸ் பை ஆஃப் எம், தட் இஸ் பை த டெஃபினேஷன் என் ப்ளஸ் எம் mod p. So that is n mod p, m mod p, that is pi of n plus pi of m, and pi of nm equal to nm mod p. So n mod p, m mod p, that is pi of n into pi of m. So for the onto, that is for any k belongs to jp, pi of k equal to k. So the kernel of P is defined the collection of the elements of J, that is n is congruent to 0 mod P, that is equivalent to, I thought, the generated by P. So when you apply the first isomorphism theorem, but J by P is isomorphic to JP, and also this JP is a field. JP is the field. Since P is a prime, P is a maximal ideal generated by the prime is a maximal ideal in J, therefore J by P is a field. So JP is a field. The ஃபுல்லாக கோ த்ரூ பண்ணிங்கனாவே உங்களுக்கு திருப்பி ஒரு கான்செப்ட் அப்ளை பண்ணுற மாதிரி இருக்கும். ஸோ அதுவே தரவாகும் டெஃபினட்டாக. So RB a ring of all real valued continuous function. M is the maximal ideal. Then there exists the gamma belongs to 0, 1 such that M equal to M gamma equal to the collection of f of gamma equal to 0. This is the idea. This is called the maximal ideal, already proved. And definition of ring embedding, that means so ring R can be embedded in a ring R dash if there is an isomorphism R into R dash. There is an isomorphism R into R dash. If R and R dash have the unit element 1 and 1 dash, that require that this isomorphism takes 1 into 1 dash. So R dash is called the overring, called an overring or extension of R. If R can be embedded in R dash, or can be embedded in R dash. So that is every integral domain can be embedded in the field. Every integral domain can be embedded in field. For example, z of x is the polynomial with integer coefficients. With integer coefficients, it's a field of fraction. Fractions, that is q of x, rational function artham, that is the rational coefficients is the example. And a comma b, this is defined that like that. And the distributed law in f, a field f is true for the definition of the a comma b equal to a dash b dash. When you define like that a comma 1, let's leave it. When the K is any field with contains D, the K contains the subfield isomorphic to F, isomorphic to F. We will take the basic definition on the field and the examples. And D is an integral domain. Suppose D is an integral domain, and for a comma b belongs to D, suppose a power n equal to b power n, a power m equal to b power m for relatively prime m and n, then a must be equivalent to b. A must be equivalent to b. So it's a very important one, that is the Euclidean ring. நேற்று a little bit பார்த்தோம்னு நினைக்கிறேன். An integral domain R is said to be Euclidean ring if for every a belongs to a is non-zero element in R, there is defined the non-negative integer, d of a, such that how to define that is for every a comma b belongs to R, both non-zero, d of a less than or equal to d of ab. And for every a comma b belongs, both are non-zero, that is there exists t comma r belongs to R, such that a equal to tb plus r, where either r equal to 0 or d of r less than d of b. So that means Euclidean ring, that ring is called, integral domain is called that ring. So for example, set of integers defined like that, d of a equal to absolute value of a. So try to satisfy that these conditions. This is the integral domain integer set of integers. D of a equal to mod a is mod a less than or equal to mod of ab, and for every elements a comma b belongs to the R. When you define that R is here z set of integers, so there is a t comma R belongs to z. So a equal to t a equal to tb plus R for every integer. Euclidean algorithm school level படிச்சிருக்கலாம், 9th or 10th வரும்னு நினைக்கிறேன். அதே மாதிரி another example, polynomial rings over the field d of f of x equal to degree of f of x ன்னு டிஃபைன் பண்ணுவோம். d of f of x degree of f of x and Gaussian integer z of I equal to d of a plus ib equal to a square plus b square. These are examples for the Euclidean ring. So the ring of integers, that is ring z is a Euclidean ring. When you define that modulus of a belongs to, that means for all a belongs to non-zero values, so that is a belongs to z by 0, z minus 0. So any integers a comma b belongs to with b is not equal to 0, there exists the q comma r such that a equal to bq plus r with the condition r is greater than equal to 0 less than mod b. So z is the Euclidean domain. Z is the Euclidean domain with Euclidean function del of a equal to mod of a. Okay. The ring of Gaussian integer is also another Euclidean ring. When you define like that, del of a plus ib equal to a square plus b square, and with beta is not equal to 0, there exists some q comma r belongs to z of I. We can define like that. So hence z of I is a Euclidean domain. The same way, polynomial ring over the field f, we can define like that. So the ring of integers of the form z of root 2, z of root 2, how to define z of root 2, a plus b root 2, the collection of a plus b root 2, a comma b belongs to z is a Euclidean ring. With the function is defined like that, del of a plus b root 2 equal to d in use பண்ணலாம், it's not a problem. This is a d of a plus b root 2 equal to a square minus 2b square. So for the beta is not equal to 0, there exists some two elements belongs to z of root 2 with the condition alpha equal to beta q plus r. This is the Euclidean domain. Euclidean algorithm அப்படின்னு கூட சொல்லுவாங்க. Non example, that is the z of root of minus 5 is not a Euclidean domain. This is the not a, it is an integral domain, but there is no Euclidean function del satisfying this required revision property, recursion property. So this is the non-example, it is not a Euclidean, not Euclidean. The example is z of minus root of minus 5. The Euclidean ring or principal ideal ring. Principal ideal ring. So the R be the Euclidean ring, let A be an ideal of R, then there exists an element A naught belongs to A such that A consists of exactly all A naught x as a x ranges over R. So principal ideal ring, the integral domain R with unit element is a principal ideal ring if every ideal A in R is of the form A equal to the generated by A some element A belongs to R. So what do you mean the principal ideal ring? Every ideal in R is of the form A equal to for some element of R generated, okay, is of the form that ideal generated by some element of R, then that is called the principal ideal ring. Okay, every ideal in R generated by some element of R, then that is called the principal ideal ring. So Euclidean ring preserves the unit element. Every Euclidean ring is a principal ideal ring. This is a very important property. Okay, this is a every Euclidean ring is a principal ideal ring. Every Euclidean ring has a unit element. There exists a principal ideal ring that are not Euclidean. Okay, the converse is false. There exists some principal ideal ring but that are not Euclidean, and the function d from or by 0 to z is greater than or equal to positive integers is often is called the degree function or norm. Degree function or norm. So these are examples for the principal ideal ring, and principal ideal rings and Euclidean ring. The examples la na vachina romba helpful ah irukum for the TRB exam. And Z is the integers, f of x polynomial over the field, Gaussian integers, z of root of -2, Euclidean ring, and hence a principal ideal ring. And a principal ideal ring but not a Euclidean ring, that is the example. Already z of root of -5 பார்த்தோம். This is the example, Månskin's example அப்படின்னு சொல்லுவாங்க. Some other quadratic integer ring. And a non-principal ideal ring z of x and z of non-Euclidean non-principal ideal ring ரெண்டுமே, that is z of x polynomials over the integers and f of x polynomial in two variable over the field. இதெல்லாம் வந்து Euclidean கிடையாது, principal ideal ring கிடையாது. And the definition of divisibility already நேத்து பார்த்தோம் நினைக்கிறேன். And GCD in the Euclidean ring, that is or be a Euclidean ring, any two elements A and B in R have the greatest common divisor D, then D is expressed as lambda A plus mu B. Lambda A plus mu B for some lambda mu belongs to R. This is a very important one. And for the R is the Euclidean. R be a commutative ring with unit element. An element A belongs to R is a unity in R. There exists B belongs to R. AB equal to 1. The set of all units in R is denoted by R star. So that means already Nathan discussed பண்ணனும் நினைக்கிறேன். Unit means not a unit element, that is R be a commutative ring with the unit elements. Unit means there exists another element for every element of R. For any element of R, that is there exists some other element. The product should be equal to 1. Product should be equal to 1. So that is unit element is the multiplicative identity 1. Unit is a unit is any element that has a multiplicative inverse. Unit element is always a unit, but there may be other unit. So R be an integral domain with unit element, and suppose that for A comma B belongs to R, both A divides B, B divides A are true, then A equal to UB, U is unit in R. So integral domain with unit element, suppose A comma B belongs to R, A divides B, B divides A is true, then A equal to UB in eduthalam, that U is should be unit in R. That is also very important idea. So in Z pathina units are plus or minus 1. And 6 comma 8 is expresses that is the greatest common divisor, that is a 2. 2 under we can express GCD, that is called the GCD, that is a minus 1 into 6 plus 1 into 8. 1 into 8. So Z of I is a Gaussian integer, units are plus or minus 1 plus or minus y. F of x polynomial over the field, units are non-zero constant polynomial. Non-zero constant polynomials. For the associate, two elements are said to be associate, means B equal to UA for some unit element in R. And this is the R be a Euclidean ring with A comma B belongs to R. B is not equal to 0, is not a unit in R. Then D of A less than D of AB. D of A less than D of AB. And definition for the prime elements. So Euclidean ring or non-unit element pi is said to be prime element. So whenever pi equal to AB, A comma B belongs to R, then one of the A and B is a unit in R. One of the A and B is a unit in R. Then that is called the prime element. Actually prime number மாதிரி வருது பாருங்க. So any composite number when you express, that is the that is a b னு எக்ஸ்பிரஸ் பண்ணா the a is at least ரெண்டே ரெண்டு டேர்ம்ல எக்ஸ்பிரஸ் பண்ணும்போது a is a unit, then that is called the prime element. That is called the prime element. Then R be a Euclidean ring, and every element in R is either a unit or can be written as a product of finite number of prime elements. Finite number of prime elements. And relatively prime, that means the greatest common divisor is unit. Euclid's lemma already discussed பண்ணனும்னு நினைக்கிறேன். That is ABC belongs to R, A divides BC, the A and B are relatively prime, then A divides C. So the Gaussian integer node nature, that is the Gaussian integer, the units are plus or minus 1 plus or minus 5. 1 plus I is a prime, and with its norm is 2 ன்றதுனால, and 3 remains a prime, that is a 5 equal to 2 plus I into 2 minus I is a factor. So that is the unique factorization theorem. RB Euclidean ring, and A is not equal to non-zero element is the non-unit in R. Suppose that A is expressed the pi 1 pi 2, the product of pi 1 pi 2 pi n. These are prime elements, that is pi 1 dash pi 2 dash pi 2 dash. That is ரெண்டுமே different இருக்கு, both are unique, that is pi a pi j are prime elements, pi j dash are prime elements of R. Then n equal to m, that is both are equal னு அர்த்தம். That is each pi I is an associate of some pi j dash, that is called the unique factorization theorem. Each pi k dash is associate some pi q. Every non-zero element in a Euclidean ring is can be uniquely written as pi a equal to u dot pi 1 pi 2 pi 2. U inறது unit, pi a inறது prime element, or a itself unit, is itself a unit element. There are maximal ideals in a Euclidean ring, that is the ideals a equal to generated by some element is a maximal ideal of the Euclidean ring R if and only if a naught is a prime element. This is a very important, maybe important one. For example, the integers prime elements plus or minus 2, plus or minus 3, plus or minus 5, and so on. Maximal ideals that is generated by some prime numbers. So, and also we know that Z by P is isomorphic to ZP. இதே மாதிரி polynomial ring over the field பார்த்தீங்கன்னா prime elements பார்த்தீங்கன்னா irreducible polynomial. Irreducible polynomial is called the prime elements for the polynomial rings over the field. And maximal ideals பார்த்தீங்கன்னா generated by f of x, and where f of x is irreducible. And f of x by f of x is a field extension, extension of f, extension of capital F. And the Gaussian integer பார்த்தீங்கன்னா Gaussian primes or prime elements. Maximal ideals பார்த்தீங்கன்னா pi, that is pi is a Gaussian prime. Z of I by pi is a finite field. இதெல்லாம் Euclidean, an element A in the Euclidean ring is the unit is the d of A equal to d of 1. This is a Euclidean algorithm. I thought 10th standard book la irukku nenikiren. Very early stage, very starting la nama discuss பண்ணோம். அது already nama discuss பண்ணது தான். The ideal contains the one unit element, means unit means then u equal to r. The units in commutative ring with unit element form an abelian group. Okay. and this is the least common multiple of a and b is denoted by a comma b is the ab divided by the greatest common divisor of a comma b. So the p is prime number is of the form 4n plus 1. The congruency x square congruent to minus 1 modulo p. And p is a prime number is of the form 4n plus 1. Then p equal to a square plus b square for some integer a comma b. So the units we can find out for the g of I. That is plus or minus 1 and plus or minus I are units. Already பார்த்தோம். The greatest common divisor for this one 3 plus I and 4 minus I, the greatest common divisor. So n of something equal to 3 square and norm of this one is a 25. So the norms are equal, so the elements associate, the one divides other. So that means 4 minus 3i divided by 3 plus 4i. When you take the conjugate, this is equal to minus I. So since minus I is the unit and 4 minus 3i, we can express minus I into 3 plus I. So 3 plus I, GCD of 3 plus I, 4 minus I is equivalent to 3 plus I. Okay, this is the idea. The same way I give the another example. The closed Gaussian integer. This is your topic, polynomial rings over the field. Okay, so படிச்சதெல்லாம் பேசிக் தான் நம்ம படிச்சிருக்கோம் ரிங் தியரியில். ஓகே, ரிங் தியரியினுடைய பேசிக் அண்ட் அதனுடைய எக்ஸாம்பிள்ஸ், ஐடியல்ஸ்னுடைய பேசிக் அதனுடைய எக்ஸாம்பிள்ஸ். ஓகேவா, நம்ம பாலினாமியல் ரிங்ஸ் அங்கே என்ன படிச்சோமோ அத்தனையும் இங்கேயே வரும். இங்கே யூக்ளிடியன் ரிங் அண்ட் பாலினாமியல்ஸ் ஓவர் த ஃபீல்டு வரும். ஸோ கொஞ்சம் தரவு பண்ணுங்க, முடிஞ்ச அளவுக்கு கொஞ்சம் படிங்க. கொஞ்சம் கொஞ்சம் எடுக்கிறேன் நான், படிச்சிட்டிங்கன்னா உங்களுக்கே பெட்டராக ஃபீல் பண்ணுவீங்க. ஓகே, எனிவே தேங்க்யூ. நாளைக்கு பார்ப்போம் பாலினாமியல் ரிங்ஸ்.